All right, pre-calculus 6.3 notes, day 3. This is our last little lesson on chapter 6, and then we'll have a quiz. We have direction angles. So a lot of definitions here. If u is a unit vector, meaning its length is 1, such that theta is the angle measured counterclockwise from the positive x-axis. That's just an angle in standard position that you've done before. So we'll go this way, and we're going to rotate counterclockwise, and we have the unit vector u. And so that's just that angle of rotation, that's all. Then we have the components of u, the horizontal component and the vertical component. If we kind of zoom in a little bit on that, then since u is equal to 1 because it's a unit vector, the cosine of theta would be x over 1, or just x. So x is equal to the cosine of theta. So that horizontal component is cosine theta. That's the value of it. That's the length of it. And then if we take the sine of y, or sine of theta, it would be y over 1 because it's the unit vector, and y is the sine of theta. So we have a triangle where horizontal component is cosine of the angle and vertical component is the sine of the angle. And then if you write it in a linear combination, remember that's when you use the special vectors I and j, then we can just change the form to the linear combination. And that is this, where we do the horizontal length times I and the vertical length times j. So the first is your component form. The second is your linear combination. It's just a changeover. You've done this, if you have negative 3, 4, then we can write it negative 3i plus 4j. Just changing from component to linear combination. So anyways, this angle is the direction angle of vector u. So you're going to be finding direction angles for various vectors. All right, so if v is ai plus bj, that just means in component form it's a comma b. It's a vector that makes an angle of theta with the positive x-axis. Then it is going to have the same direction as u, meaning this is theta, this vector makes an angle of theta. And so you can write vector v as the magnitude times the unit vector. So it's just saying that I've got, think about your x and y axes. So I've got this unit vector, and it has the same angle. And so if vector v is 5 times, or we'll take 3 times longer, then I can just take 3 times the component form of vector u, and I will have vector v. Just take the magnitude times the cosine theta, sine theta component form. That's all you have to do. Because of this right triangle, we have the relationship that the tangent of theta is sine theta over cosine theta. Or if we are talking about AB, then that means this is B over A. So we have the tangent is sine over cosine, and so then the tangent is B over A, and we can find theta by doing the inverse tangent of your vertical component over your horizontal component. But we do have to consider what quadrant it's in. But and add 180 degrees as necessary, or 2 pi, to get it into the quadrant that the vector's in. So it looks like a lot of stuff, but it isn't that bad. Let's just get to an example, and we can kind of refer back to it a little bit. It says find the magnitude and the direction of each vector. Well, this is in a linear combination. In component form, it would look like this. You find the magnitude the same way you've been finding it. It's the square root of your horizontal squared plus your vertical component squared. That's your magnitude. And you get 9 plus 9, which is 18. And that's 9 times 2, so it's 3 root 2. And that is your magnitude. And then if this is A and then B, we find the angle, tangent of theta is your B over your A, and theta then is the inverse tangent of 3 over 3. And that's the inverse tangent of 1. The problem with inverse tangent is that it will only give you an angle between negative pi halves or negative 90 degrees and 90 degrees. Because inverse tangents, they have that restriction on them. So when you do the inverse tangent, here you do it in degrees, you actually get the right direction angle because 3, 3 plots to the right 3 and up 3, and it is in quadrant 1, and this is then 45 degrees. So you get the correct direction angle because it's in quadrant 1. Just if you do inverse tangent, you get 45 degrees, that's the correct angle. We're going to see as we change into part C that we're going to have to do something to that to get to the correct angle. In part B, it is already in this kind of form. It's already broken into, the magnitude times this cosine theta I sine theta I. It's already broken into that. And then you've got this magnitude on the outside. So if you look at that, the magnitude is just 5, and theta is 120 degrees. That it gives you the magnitude and the angle, just like that. Now we can go through the motions and check it. Cosine of 120 is negative 1/2. And sine of 120 is root 3 over 2 from our unit circle. So we've got a negative 5/2 I and 5 root 3 over 2j, meaning that the component form is this. To find the angle, you've got your component form right here. Theta is the inverse tangent of your y-coordinate over your x-coordinate. And that is the inverse tangent of a negative root 3. Now, if you do the inverse tangent on your calculator of a negative root 3, it's going to give you an angle between 0 and negative 90 degrees. And it's going to give you a negative 60 degrees. That doesn't match the angle because if you go to plot a negative 5/2 and then the 5 root 3 over 2, if you go to plot it, you end up in quadrant 2. The angle that the inverse tangent gives you when it's negative is this angle. But inverse tangent, to get to the next time it's going to happen, you always add the period, which is 180 degrees. So you have to realize that that vector is in quadrant 2, and you add the 180, and that is your direction angle. So you've got magnitude and direction, which we said that's what you expect from the get-go. But this verifies all that. All right, let's look at part C. The component form of this is -3, 4. So the magnitude of vector v is just that square root of a -3 squared plus 4 squared. And you get 9 plus 16 is the square root of 25, which if you think of it as a triangle, it's a 3, 4, 5 triangle. And so that is 5. The angle, the direction angle, we get by taking the inverse tangent of your sine over your cosine, or your y over your x. Now, if you put this in your calculator, since it is negative, it is going to give you an angle between 0 and -90. And it comes out a negative, I didn't do it to 3 decimals. I have to actually calculate it. Let me see. Inverse tangent of 4 divided by -3 is a -53.130 to 3 decimals. But if you go to plot this, you're going left 3 and you're going up 4. And that vector is a quadrant 2 vector. You are getting this angle right here, the -53. You must add 180 degrees to that in order to get the correct vector. And when you add the 180, theta is actually 126.870 degrees. And that is your correct direction, and this is your magnitude. So you gotta, watch out for this. Make a note to go, remember, I might have to do what? Add 180. You might have to add it twice to get to the correct quadrant. You might have to add 360. Because the angle needs to be a positive angle, and so you can't use a negative angle for the direction. It's got to be positive. So if it's in quadrant 4, you're going to end up having to add 180 twice or add 360. All right, so on the back side, find the component form given its magnitude and the angle it makes. Well, you take the magnitude times the cosine of 45 degrees plus the sine of 45 degrees. That gets you your linear combination. And so 45 degrees, if it's not one on the unit circle, then use your calculator. But these are unit circle values that you know. And as you distribute the 2, you get a root 2i plus a root 2j. And so the component form is root 2 comma root 2. That is your component form. This is component. This is your linear combination. You can actually go right to this formula. I just thought of it the other way. This is on the front. This is, except for I want these to be component forms. And so we could have just gone right there. And you end up in the same, you change them to root 2 over 2, you distribute, and you get right to your component form. So same thing, just, and actually a little more direct. All right, example 3, find the component form of the vector that represents the velocity of an airplane descending at a speed of 150 miles per hour. Speed is the absolute value of velocity. Velocity has direction to it. Speed is just positive. So this is your 150. At an angle 60 degrees below the horizontal, this is supposed to be 60 degrees. So we modified, I think, a problem. It used to be 20 degrees. I mean, so 60 degrees would look more like this. And so find the component form. So if we go to, we want the magnitude of whatever we want to call the vector times cosine theta sine theta. But theta has to be the angle starting from the positive x-axis and rotates all the way to here. Rotates all the way to there. And so theta needs to be 180 degrees plus the 60, which is, so theta goes all the way from here to here, and it's 240 degrees. Well, the magnitude is the length of the hypotenuse. It is 150. And then we need the cosine of 240 degrees and the sine of 240 degrees. Which, if this was not on the unit circle, then you use your calculator and just make sure it's in degrees if you've got degrees there. But since it is a unit circle value, cosine of 240 is a negative 1/2, and sine is a negative root 3 over 2. And so you get a negative 75 and a negative 75 root 3. And it didn't, find the component form. And they distribute the 150 in and work it out, and they just give it as in that form. So that is component form. If they wanted linear combination, you need to change it to negative 75I minus 75 root 3J.